We've discussed central tendency, mode, median, and mean. Our attempt to come up with a value that captures the central point, the representation of our data, so then it gives us that numerical summary of our data. But a single score does not really capture the full sort of picture of our distributions. For example, let's look at what happens when instead of just doing histograms of all the caffeine content regardless of restaurant, we break them up into different restaurants. What I've done is created separate histograms for just Applebee's, just Arby's, just Burger King, and just Hardee's. Over here, if we look at the means, we will see with the exception of Arby's, the difference between Applebee's, Burger King, and Hardee's, they're all very, very similar. There's just not much difference in means. But when we look at the histograms, we can see that there's actually quite a bit of difference in the distribution of the data, right? And see that for Applebee's, most of the data is clustered strongly in this sort of 39 to 42 range with only a little bit of variance to either side. Yes, there is sort of a symmetrical pattern out here, but there isn't a very high frequency. Whereas when we're looking over here at Burger King, we see that there's a little bit more of a range, and they're all about equal to each other. We're not going, we don't have this big peak. And then lastly, if we look at Hardee's, we can see that there is a much larger variation, much larger range between the low and the high, and the peaks are not as clear. Right? So while the mean can tell us a lot about the central tendency, we're missing something. We need something else that can tell us more about the shape of the distribution. What we're looking for is a measurement of variance. How much does our data vary across the mean? Is there all the data clustered together? Is it spread out? Right? Variance can give us a much more complete feel for what our distribution is. So, how do we calculate variance? Well, the first step with any data set is to calculate a mean. In fact, from now on, whenever you see a list of numbers, I want you to start thinking about calculating a mean. See a list of numbers, calculate the mean, right? Look at a menu, see the prices, calculate the mean. Okay? Always be thinking calculate the mean. So we start by calculating the mean. And then what we're going to do is we're going to take that mean and we're going to go back and we are going to subtract it from each score in the data set. So what we're getting is the difference between the score and the mean. However, since half of our data is going to be below the mean and half of our data is going to be above the mean, we're going to have half of our data is negative, half of our data is positive. If we try to add up that difference, it's going to come out to 0. So in order to alleviate that, we square the difference. By squaring the difference, we get rid of those negative signs and we get a magnitude of the difference between our scores and the mean. The next step is to take those square difference scores and add them all up. We're going to sum them all up. This produces what we call a sum of squares. This sum of squares is going to be a very important number in this class. We're going to be using it a ton. So it's really important to begin to understand what it is, right? The sum of squares is the difference between each score and the mean squared, and then we take each of those square differences, we add them all up. Once we have the sum of squares, now all we have to do is divide by the total number of scores or observations we had. Let's look at it in equation form. So this is exactly what we just talked about. We're going to take each of our scores represented by x, and we're going to subtract the mean. Once we've done that, we are going to square that value. We then use that summation sign that tells us to take x minus m squared, and then we're going to add up each of those. Then, at the end, we divide by the total number of observations. This is the formula for variance. Let's take a look at it in practice. So if we have 10 cities and we have data that tells us the price of a gallon of milk across those cities, we need to determine the variance. Well, what's the first step? Well, remember, you see a list of numbers, you need to get the mean. Well, we know how to calculate the mean. We take each of the scores, we sum them all up, and then we divide by the total number of observations, which gives us a mean of 3. Next, we're going to have to take that mean of 3, and we're going to have to subtract it from each of the data points. We had 10 data points, so we track the mean from each of those 10 data points. We then square that answer, and we add each of them up. If you go through and do the math on this, you'll find that our sum of squares is equal to 10. Lastly, we divide by the total number of observations, which was 10, so in this case, we get 1. One problem we have is that the variance is squared, and that's usually not what we need, right? If we have the price per gallon of milk, variance is the price per gallon of milk squared. We have the variance of, say, caffeine, it's the variance of caffeine squared. What we usually want is some sort of measurement of variability that is in the same units as our observation. So we have to get rid of the square. It's real simple. All we got to do is take the square root. When you take the square root, you get rid of that squared units, you're back to the original units, and that's what we usually use when we're doing calculations. Variance is when we have squared the units. The standard deviation is after we take the square root. Let's take a look at calculating variance and standard deviation in Google Sheets. Again, pretty straightforward. So we have Applebee's, Arby's, Burger King, and Hardee's. We have the means already calculated. We learned how to do that in the last video. Let's look at variance and standard deviation. For variance, right, we're going to click on the cell we want to do it in. We'll hit the equal sign, right? Tells us we're doing an equation. And variance is just VAR. That's all I do. Again, we do the parentheses. In this case, we're only going to select the data for Applebee's. That's all we want it for. We press enter. There we go. Let's do Arby's. So it's VAR. And again, we have to use the parentheses. Select the data for Arby's. Press enter. For Burger King, equal sign, VAR. Put it in parentheses. We have to scroll a little bit, but we'll select our Burger King data. Okay. And then Hardee's, same thing, VAR. And then we come down to Hardee's, and we select Hardee's data. And there we have our variance for each of our restaurants. And already you can begin to see some big differences, right? Remember how we talked about with Applebee's that the data seemed to be a little more clustered around the mean, and for Hardee's it seemed to be a lot more spread out. And look, it's exactly what we see in the variance metrics. Even though the means are nearly identical, right, we can see that there's actually a big difference in how the distributions look and their variance. Let's do standard deviation. So equal sign, in this case it's STDEV. We do the parentheses, and then we select the data we want to calculate it on. Right? That'll give us the answer. Let's try Arby's. STDEV, the parentheses, and then we select Arby's data. We can also use the square root of the variance, right? We don't have to use this function. It's going to give us the exact same value, but instead, for example, for Burger King, if we did equal sign SQRT, tells us it's the square root, and all we're going to do is we're going to select the variance value next to it. We get the standard deviation. Let's try it again. SQRT, parenthesis, select the variance value, and there we go. And we can again see that variance and standard deviation gives us a lot more information about the shape of the distribution, right? Before, the means didn't tell us a whole lot. They looked very similar to each other, but with the variance, we can see there's actually a big difference in the shape.